Here's another example asking us to use a linearization to estimate the value of 1 divided by 5.0026. So again, linearization is just a fancy word for a tangent line equation. So we're going to try to write the equation for a tangent line. But notice first that 5.0026 is a number that is very close to 5. So we're going to try to write the equation for the tangent line at a equals 5. So this is telling us that we're going to let a equals 5. My 5s are looking bad today, sorry. There we are. And because we're looking for the value of 1 divided by 5.0026, then we're going to let our function be 1 divided by that ugly number, 1 divided by x in this case. So we're trying to write the equation for the tangent line to the function 1 over x at a equals 5. So we need to start with a point. And we have basically the x value for our point. We just need the y value. So the y value will be found by plugging 5 into the function. So that means that our point is going to be 5, 1 over 5. Next we need our slope. And our slope will be the derivative of this function. Now remember, 1 over x can be rewritten as x to the negative first power. And that's probably the most efficient way to compute the derivative because now we can just use the power rule. The derivative of x to the negative first power is negative x to the negative second power. And by doing that rewrite, we avoid using the quotient rule. It would not be very efficient to use the quotient rule in this case to find the derivative. Now, I would recommend before we plug in 5, let's go ahead and rewrite this derivative. Negative x to the negative second power is really the same as negative 1 over x squared. And that's going to be a lot easier for us to work with now that we're going to plug in 5. We're substituting 5 into our derivative in order to find the value of the slope at that point. So our slope will be negative 1 over 25, negative 1/25. So at this time, we have our point, we have our slope, so we can go ahead and write the equation for our line in point-slope form. That'll be y minus 1/5 is equal to negative 1 over 25 times the quantity x minus 5. And if you add the 1/5 to the other side, we'll get the equation for the tangent line. And as mentioned in some of my other videos, many textbooks will go ahead and replace the y with L of x. So you'll often see this written in textbooks as L of x is equal to negative 1 over 25 times x minus 5 plus 1/5. So this isn't the answer to our question, but rather this is the tangent line equation. So remember, the entire idea behind a linearization is that we're taking a complicated, ugly function, f of x, and we are estimating that function using a tangent line equation. So we say f of x is approximately L of x. So in our case here, our complicated function was 1 over x, and we're saying that we can estimate that function 1 over x with the equation of the tangent line that we just wrote, which was negative 1 over 25 times the quantity x minus 5 plus 1/5. And this tangent line is going to be a good estimate for the function when x is near 5. So, because we are looking at the value 5.0026, and that indeed is near 5, then we can estimate 1 divided by 5.0026 using this tangent line. So we're basically just substituting 5.0026 in for x. And then you'll go ahead and get out your calculators and input the right-hand side here. So pause the video, of course, at any time to make sure you're putting everything in the calculator correctly. And this is going to equal about, let's see, 0.199896. So this value, 0.199896, is our estimate for 1 divided by 5.0026 using our tangent line. And just as a side note, if you wanted to get out your calculator right now and actually test this out and actually type in 1 divided by 5.0026, you'd see that that will equal about 0.1998960,541 is what my calculator is spitting out to me. And then you can see just how close our estimate was. Our estimate of 0.199896 was a pretty darn close estimate of the actual value. So in this case, our estimate is a fairly good estimate. But again, that has to do with the shape of the graph as well as how close our x value was to 5.